It's 2 a.m. My wife and my 5 children are sleeping peacefully, as was I before my pager goes off. I leap up, I run downstairs, I log into my computer. Amazon's broken. I join a conference bridge with 30 other engineers frantically trying to discern what's went wrong and restore it as quickly as possible. Today, I am call leader. It's my responsibility to manage this chaos, to resolve it as quickly as possible. In this outage, there were several things that went wrong, as is often the case for any interesting outage or disaster. It's a confluence of unfortunate circumstances that cause a massive failure. In this case, this outage lasted 45 minutes until we were able to diagnose it and restore it. And Amazon lost over $1 million in revenue over that time. This highlights to me a truth that I learned operating systems like these. And that is that we rely on systems, on an internet, on software that will fail. It's not a question of if, it's a question of when. And this has changed our thinking and how we prepare for this and what we do to ensure that when failure occurs, the right things happen. Unfortunately, there are many examples of failures such as these. I update this slide fairly often, and there's no shortage of things to choose from. Coming from an e-commerce background, I'm familiar with days like Black Friday or Cyber Monday, days of trepidation where anything that can go wrong will, preparing for months in advance. But what about your flight that gets delayed? What happens if you try to pull money from an ATM and you can't? What happens when the service you rely on to communicate or to collaborate is not available? These have real impacts to our everyday lives. And in fact, as we as a society rely more and more on the internet, more and more on online services, this pain will only become more acute. Everything will be an online business. Everything will move toward being an online service. You don't like the DMV today, you don't like government services, imagine what happens when they fail. And so what has brought us to this point? Why is it that we're seeing more and more headlines in this regard? In one part, it's because it hits us closer to home. But on the other side, there's been some changes in how we build our software. Let's talk about the way software used to be built, and I'm going to oversimplify things here. We had some data centers. Within those data centers, we had hosts, we had servers, we could hot swap RAID drives. We had the illusion of control of that failure. And we had redundancy so that we could shift between data centers if we needed to. Our applications themselves were a bit more straightforward. We had a front-end tier, it was horizontally scalable. We had some business logic to handle to make sure the right things occurred. And we'd leave a lot of the heavy lifting to the database or the persistence tier. Let's contrast that with what our systems look like today. This is a picture I lovingly refer to as the microservice Death Star. This is Amazon.com. This doesn't include AWS. This doesn't include Kindle. And this picture's 10 years old. What are we looking at? Well, each of these is a host, a server, a database. And each of these lines is communication between them. So right here, you probably look at this and say, how do I make sense of this? What are you showing me? And unfortunately, that's how a lot of engineers react too. What is going on here? And if somebody tasks you to say, tell me everything that might go wrong in here, you might have a difficult job. In the past, we could have an architect or a team that could keep the whole system in their head, that could think through the failure modes, and we could brute force test them. In a world such as this, no one person, no one team can keep this all in their head. It's too complex. And in terms of taking the old approach of testing all of the things that could go wrong, well, the combinatorial explosion and all of these side effects and all of these potential combinations of failure, the sun would burn out before we finished testing this system. And we deploy software not on the order of weeks or months, but on the order of days and hours. And so the system that we tested yesterday is not the system that we're operating today. These are the struggles in building reliable systems that we faced at companies like Amazon and Netflix. And it helped us to prepare for how to deal with this kind of chaos. And so this has really given birth to a new discipline of chaos engineering. The crux of chaos engineering is we want to go out and proactively cause failure to see how the system will behave. We want to shut down hosts. We want to fill up disks. We want to create memory leaks. We want to sever network connections so that we can understand the soft and weak spots within our system. This will help us understand how we look at our system. There's so many lines of code, so much depth of complexity that happens that the code that we write or operate is but a small piece of that. And the opportunity to really understand how the system fits together and works is critical to being able to keep it up and highly available. And so the definition for chaos engineering is not let's go randomly break stuff. It's thoughtful, planned experiments. We have a hypothesis. What happens if US East 1 goes down? What happens if we can't get data out of a cloud storage system? What happens if our internal identity service fails? And what will the customer experience be? And from these, we have questions about how to measure it. What happens when these fail? Can we detect it? Do we see it? Now, one key analogy I rely on here when I'm home for the holidays, when I'm talking to my mom or my grandma, is that of the vaccine. I know vaccines have gotten a little bit of press the last 10 years, but if you go back 200 years and I said, hey, I'm going to inject you with this disease, is that cool? You probably would have gotten some pushback. That's about where we've been for the last 10 years of chaos engineering. You want to do what? Why? But there's a lot of evidence that supports vaccines and this approach. I like to draw the analogy of the body. When we're dealing with a foreign agent, our body is learning how to combat that. Our systems are learning how to reject that and prevent it from reoccurring. It doesn't mean that that disease or foreign agent won't arrive again, but when it does, the body's more quickly able to neutralize it and restore itself to a healthy state. This is exactly what happens in our distributed systems and with the teams that operate them. That ability to understand how the failure manifests. Can the software heal? Do the teams know how to react to it? Allows us to uncover these issues and strengthen the immune system so our service isn't out for the weekend with a flu. The other key difference to your classic operations or site reliability engineering approach is that in those worlds, after something's gone wrong, how quickly can you fix it? It's a race to restore service. With this approach, and that reactive approach just wasn't sufficient for the types of high availability goals we had at Amazon and Netflix. To reach 4 nines or 5 nines of uptime, to have less than an hour of an outage throughout the course of a year, requires being proactive. It requires seeking out and finding issues that would be disasters, that would be large outages, and fixing them before they occur. So how do we do this in a safe and controlled manner? I mentioned this isn't, just running in and being a cowboy, cowgirl, just shooting hosts. We want to be thoughtful about it. And so one key concept is that of the blast radius. We always want to run the smallest experiment that will teach us something. If we can run an experiment on a single user, usually mine, or a single host, a subset of traffic, maybe even the staging environment or a dev environment to begin, then we're taking on less risk to understand this problem and to resolve it. And from that, we can go uncover these issues. And so there's 2 outcomes at every step. 1, something didn't work the way we expected. It failed. We couldn't detect it. We couldn't monitor it. We didn't expect it. There was something that didn't go right. Cool, we're done. We've learned something about our system. We've uncovered an unhealthy behavior. Now we're able to go diagnose that. We're able to go debug it and fix it and make the system better. Or things behave the way we wanted to. Now we can expand that blast radius. We built trust and confidence that the system can fail at a low level. Now we want to fail it at a larger scale. And at each step, we're going to continue that process until we've run it in production at 100%. And that's important because we learn different things at different scales. At the small scale, do we handle a null? Do we have the right fallback? Have we thought about how our code handles this type of failure? But at the large scale, we're testing our system under duress. Do we shed traffic when we're underwater so we continue fulfilling customer requests? Do we back off of a downstream dependency that is underwater so we don't further cause them issues? Are our timeouts, our thread pools, and our resource constraints tuned correctly? Here's my hint. They're often not. There's often so much devil in the details for how we configure our environments and how we operate them. Whether it's the cloud, whether it's Kubernetes, whatever the case may be, making sure that we've set it up correctly so it does what we think it will do is a lot harder than it sounds. So let me take you briefly through an evolution of chaos and what's happened over the last 10 or 15 years in this space. In the beginning, the cloud was new, and we were migrating to it. It was a new world to operate in, one in which your host could be taken from you at any time, one where it could be rebooted and replaced with another. And so how did we prepare for that? Well, we said, look, let's get comfortable with our host dying, with our host failing, with them being replaced. And this helped us to prepare for that. Now, it didn't require a lot of maturity to get started here, and we were able to pick it up off the shelf and get some value right away. We at Gremlin, we believe firmly that this is a great place for companies to begin. And so we actually this year released a free product so that people could shut down their hosts and max out CPU so that they could get their hands dirty and really understand what chaos engineering was about and get some value from the approach. But we quickly hit the limit of that naive approach. And so the next question becomes, can we handle the bad things that happen to us? Now, this could be CPU maxed out. This could be a disk filling up. As silly as it is to say, every company I've worked for and every company I've spoken to has had an outage because a disk filled up somewhere. It might be trivial, but if we haven't tested it, if we haven't found those edges, we may be surprised. And so this helps us to be thoughtful about the infrastructure things that can go wrong. Disk, CPU, memory, processes die, time fails. To do this well, we have to take a more disciplined approach. It can no longer be, we're going to randomly break stuff and see what happens. Now we want to measure it. We have this hypothesis that's come into play. And a key part of this is actually teaching us how to operate our software. Many teams don't know they have gaps in their monitoring or places in which they're flying blind, so to speak. And so that ability for us to refine that, to learn that, and to practice that gives us an edge, helps us to understand and prepare. Now, as we continue on and teams get more mature, the question is not, should we handle another service's failure? And I'm here to tell you that. If you think it's okay for you to tell your customers that Amazon is at fault, or Azure's at fault, or your third-party SaaS is at fault, I'm sorry to say you're wrong. We have to take responsibility. Our customers don't care whose fault it was. They care that the service or the website or the product that they paid for didn't work. And so the question becomes, can we handle those failures? And that becomes a little bit more difficult. Now we need to be going into the world of distributed systems. We need to be preparing for these large-scale events. We run these exercises called game days, where we get many teams in a room, where we talk about what could go wrong, and then we run those exercises. We evacuate a region. We drop all traffic to S3. We make our internal identity service twice as slow to see where it tips over and how it behaves. Now, this requires a little bit more maturity. We have to understand how the network works. We have to understand how our software communicates. But again, that's a value add. That's an important learning that helps us to deeper understand our systems so that we can build them better and architect them better. And then we move beyond the infrastructure and the platform concerns into our applications. At the end of the day, our applications are where customers are won and lost. If we do a poor job giving them a good experience. If we throw an error right in front of them, if they're going to watch a movie and we say, oh, you know what, we can't recommend for you this other movie, so everything fails, they'll be unhappy. They'll want more. And so what we can do is we can be more precise in our experiments. An example, I was part of an outage at Netflix, and a good friend of mine was following along as we were resolving this incident. He had a good idea what was broken, and he ran an experiment during this incident against only his user to test his hypothesis. It failed the way he thought it would, and he found the logs and was able to dig into the code and find the underlying contributing factor for this outage. So before we had completed mitigating this issue and restoring the system, this engineer had a pull request ready to fix it. That's the kind of power that can come when it's easy and it's safe for people to answer these difficult questions in our systems, that we can get to the heart of the failure, uncover it, and strengthen it. And once we've done this, it gives us an opportunity to automate these types of experiments, these types of failure modes. We want to run them often and frequently so we don't drift back into failure. And this helps us to harden our builds and harden the applications and services that we're deploying tomorrow. Another important analogy to draw is that of the fire drill. Who's grown up participating in fire drills here? Who went outside when the fire drill happened earlier? Yeah, a bunch of us didn't, right? Maybe we listened well, maybe we didn't. But the truth is, fire drills help to prepare us for urgent events. Had there been smoke or fire, you guarantee people would have known the right thing to do. This also applies in our distributed systems. Unfortunately for our industry, the on-call training most engineers receive, which is what I got, is here's your pager, good luck. You're smart, you'll figure it out. We had a run book over there, but it's out of date. That's not the world that we want to live in. That's not a prudent decision. We want teams to practice during the day when the caffeine's kicked in. We want them to have the opportunity to ask questions, to build the muscle memory so that when something urgent occurs in the middle of the night, they can react in that calm, safe way. They know how to handle it. That's not the time to run around with our hair on fire. It's the time to calmly and carefully evaluate what's happened and fix it. And so at the end of the day, we as a society are only going to rely more and more on the internet. Our systems are only going to get more complex, and there will only be more chaos within them. So rather than turning a blind eye to it, rather than saying to ourselves, failure might not happen to me, we instead need to address it head on. We need to embrace the chaos. We need to apply engineering discipline in order to tame the chaos within our systems. And ultimately, this is why I founded Gremlin. It's great that Amazon and Netflix are up, but it's a better goal for society to have a more reliable internet. And that's what we care deeply about. Thank you.